Nathalie Wahl, Copenhagen, to speak on higher strings.
Okay, thank you to the organizer for the invitation, to Igor for the introduction. There's a whole hour before going to the pub, I'm sorry. I'll try to, I don't have any beer, I'll try to do what I can to entertain you until then. Sorry? Make you want to have a drink. I know you don't need any help.
It's getting a bit delicate.
Sorry. Okay. So I want to talk about higher string topology. Let's start with string topology. So this is something that goes back to Chas and Sullivan. And so it's about, and I'm going to talk about string topology on manifold. So I'll have a manifold. This is a closed compact manifold of dimension n, and n is a globally fixed constant for the torque. And if you have a manifold, you may look at its loop space, the free loop space on the manifold. This is the maps from the circle into M. And then you may wonder you may want to study this space. And one way to study it is to look at what structure it has. And so what Chas and Sullivan did is to define the product. And the idea is sort of if you have a loop somewhere in the space and another loop, you'd like to multiply them. If they don't intersect, it's a little difficult to multiply them. So you say, well, say they maybe intersect. They do actually intersect. If they did intersect, you could multiply them as you usually do with loops by just taking the concatenation of loops. So what this comes down more precisely in practice is what you get is what is this Chas-Sullivan product, and it goes from it takes chains. It's going to take not going to be defined on the space level as such because loops don't always intersect. But what you can say is if you have a chain of loops, so think of it as a family of loops and another chain of loops, another family of loops, you can first intersect the sort of the chains you get by looking at the base points, the evaluation at 0. You intersect these, and where the two chains intersect, you do your loop multiplication. What happens is that you land in C star minus n of the loop space where you have lost the dimension of your manifold in dimension because you have done an intersection. This is because of the intersection product. And otherwise, so you do an intersection of the base points and then you do a concatenation. And if you look at how this combines with, you have another structure on the loop space, which is the circle action. So you have an S1 action, which just on LM, which just rotates the loops. If you combine these two things, what you get is a Battanin-Vilkovisky structure on the homology of the loop space up to some degree shift. Okay, so that's the Chas-Sullivan original product, and then you can ask one question. Is there more? Are there more such operations? And I'm a sort of one of these operatic type of person. I like spaces of operation, and I'm sort of topologist, so I really like actual topological spaces if possible. But we're going to get in algebra in a second. But let's sort of ask the question more precisely like this: what space X, P, Q define, and I'll say non-zero maps, because zero maps are easy to define. So non-zero maps. Like they say on the chain level, chains of X, P, Q, tensored chains of the loop space tensored P times, two chains of the loop space tensored Q times. So I'm looking for a prop of operations with, so for each P and Q, I'd like P, whenever I have P inputs and Q outputs, I want a space or chain complex of operations. Okay, so that's the question. So I was thinking I'd do like Boris, I'd tell you about the past, the present, and the future. So we'll start with the past, and it's of course a very sort of personal thing, what's past, present, and future. So I mean, it's not a very fair notion of past. But anyway, we could take X, P, Q to be the disjoint union of over genus of B diff of a surface of genus G with P plus Q boundary component. This is also equivalent to disjoint union of moduli spaces of Riemann surfaces with genus G, P plus Q boundary components. So this is surface. Think of it as having P inputs and Q outputs, and you'd like to say, well, this is the correct type of thing to act on strings. It takes, you see the strings here, they're here, and you have sort of end strings. It feels like the right thing to define operations. So this is something which is not easy to do in practice, but was done by Véronique Godin. So this is, this was why I said past is a little bit unfair. There's a very recent upcoming preprint of Cooper giving a simpler proof. But I mean, it relates also to work of Costello, Kontsevich, Sabelman.
Yes, Björn Cooper.
Thank you. Cooper's.
I don't know who you're talking about.
Yeah, the guy yes, that same person, yes. Yes, you know. Good, thank you. Okay, so this is sort of the first wish people had, is to say, well, a proper space of operation should be the moduli space of Riemann surfaces, and I'd say this is also has been a big motivation for me, because if the moduli space of Riemann surfaces acts here, then in some sense, I mean, we know not as much as we would like about this, the chain complex or even the homology here, and this is giving us representations of it. And so this is a very interesting situation. Okay, so I want to talk about the present. So this is this. Present is this talk, of course. So we're going to take X, PQ in a bit to be also this joint union of a genus, but it's going to be some sort of Sullivan diagrams here, G, P, Q. This is so I'll define this in a bit, but of course, I mean, it will come with a map. So I'll define operations, and I'll define them from these Sullivan diagrams. In particular, I can compose. I will have operations from moduli space. The fact of the matter is, the ones I define, they are really parameterized by these guys. That's not something I chose. This is how it is. So so this is a space. In a bit, it'll be a chain complex of Sullivan diagrams. And here there's, I should mention work of Kate Poirier, who's a student of Sullivan. I guess Sullivan himself probably thought about Sullivan diagrams acting in over the last many years. And I have joint work with Craig Westerland, and then with Ralph, who's here, and Nancy Hingston. Okay, so that'll be what I'll mostly be talking about, but let me say a word about the future. Well, there's a space we don't quite understand yet, which is sort of commutative Sullivan diagrams, and this sort of ongoing work of a student of mine, Angela Clampt. Again, there's a map, and I think of these things as better and better approximations of what is really parameterizing these operations. Good. So in the sort of, there are two approaches to do such construction. There's an algebraic one and a geometric one. The geometric one is the one I explained a little bit. Is the original approach of Chas and Sullivan, is to say you have a chain of loops and you have another chain of loops, you intersect them, you concatenate them, you actually do things with loops. It's tricky. This is easier. Algebraic one, so I'll start by the algebraic one, and then I'll come back to a geometric approach at the end. So what's the algebraic way of approaching this? So if you have it only works for simply connected manifolds, but that's already a large class of them. You ask John Jones, and he tells you that if you take the Hochschild homology of the cochain algebra of a manifold, or space, any space, one connected space, this is isomorphic to the cohomology of its free loop space. So this is the cochains. The cochains on the manifold. Okay, and what do we know about the cochains? Well, I don't know, but it's one thing we know about at least the cohomology of a closed manifold is that it is a Poincare. It satisfies Poincare duality. So it's an algebra with a non-degenerate. It's not any algebra. It's an algebra with a non-degenerate pairing. It's something I'll just call a Frobenius algebra. Some people call this a Poincare duality algebra or whatever you like. Okay, so we know this about the cohomology. Now we should put the chain. Well, the chain should be some homotopy version of this. And the idea of the algebraic approach is to say, well, we have the Hochschild homology. What do we know about the Hochschild homology of structures on the Hochschild homology of algebras in general? There's not that much we can say. There's at least there's this B operator which corresponds to rotating the loops actually on this side. So it exists also algebraically here on the other side. But in general, you don't have much structure on the Hochschild homology of just an algebra. But we would like to use this extra information to produce more operations. So here's a a tool you may, yeah. So I mean, you want the sort of an induced structure on the Hochschild chains of the cochains of him. So here's a tool you may use. A theorem. So say let E be what I call a prop with a infinity multiplications. What is this? E is a symmetric. A prop is just a symmetric monoidal category with objects and natural numbers. Is what one of these things of operations. For every PQ, I have something like this, and it composes. And I have a tensor product. I can sort of add operations, put them next to one another. And having an A infinity multiplication just means that in the prop, part of the prop is a multiplication, which is a map from the prop of A infinity algebras. That means algebras over these guys, people who have these operations, they will be algebras in particular. And in particular, they will have a Hochschild complex. So I'll be able to talk about the Hochschild complex. So suppose I have one of these objects, then there is another prop. A prop which is some prop of natural operations on the Hochschild complex of E algebra. So defined. So let me say how it is defined. Oh, one way of you can define it explicitly as. So I have to tell you what the operations from P to Q are, and there are some sort of iterated co-Hochschild construction of a Hochschild construction which you apply in some manner to your prop. More precise, I mean, if you want to write this explicitly, it's going to be some product over J1, Jp of a direct sum over Q1, K1, Kq of the morphism spaces in your prop, J1 plus Jp, K1 plus Kq, and then with some, so this is as a graded vector space, well, up to a degree shift, so as a vector space, and then with a differential, which is the differential of E, a certain Hochschild differential, which sort of sums over doing some multiplications here, and a co-Hochschild differential, which sums over co-multiplication. So it's an explicit guy, and this one, so which acts naturally on the Hochschild complex. I'm going to run out of space. So it acts naturally on the Hochschild complex of algebras over this prop. Algebra, so it gives me maps as I was looking for. Let me say one extra word about this is that this is actually it's in fact it's the chain complex is the chain complex of all natural operations, not on the category, not on the chain, not on the on the Hochschild complex, not of just E algebras, but sort of generalized E algebras, which are of any functor from E to chain complexes. So just there's a characterization of this guy in terms of being all the natural operations in some. It's a home complex in some very precise sense, but this is in some sense not that relevant right here. Okay, so where are we? We wanted to build operations on. We wanted to build string topology operations, or at least algebraic versions of string topology operations. And we said the cohomology of the free loop space is this Rothschild homology of the cochains on the manifold. Cochains on the manifold is some sort of Poincare duality algebra, Frobenius algebra. And so what we want to do is to input this into that machine and then try to read off what it tells you. So left to choose an E, a prop E that acts on cochains of the manifold, and then read off, and then try to read off what we get. Okay, so I propose two solutions that will give the same answer, but the sort of the first solution is just, I mean, it's in some sense it's nice and clean, is to just go over the rational numbers and then to use work of Lambrechts and Stanley and say, well, actually cochains on the manifold is as a DG algebra, you can make it quasi-isomorphic to a an actual strict Frobenius algebra, like but the DG, strict DG Frobenius algebra. So this homotopy structure, you can actually make it strict if you're willing to go over the rational numbers. So this is one possibility. Here's a second one. Second solution, which I think Bruno will prefer. Where's Bruno? Yeah, maybe. Solution is import the Frobenius structure of the cohomology of M to a Frobenius infinity structure on the cochains. And here I don't really, that Bruno might not like, I don't really care what this is, and I also don't need this to be the biggest thing, anything that is where this is something which is equivalent, some sort of fatter version of my original problem.
What's Frobenius structure on? Isn't it the other way around? That there'll be a Frobenius infinity structure on the cohomology and a Frobenius structure on the original. I mean, it's usually the smaller thing that has the homotopy structure.
The smaller thing, usually.
Because there could be secondary operations.
There could be. I'm just saying, do some, I mean, these two things are quasi-isomorphic. One of them has a strict Frobenius structure. I can't import a strict Frobenius structure, but see the strict Frobenius structure as a homotopy Frobenius structure and pull it back. I agree, this could be a very wrong thing to do. I mean, I might be missing.
It just looks like you've exchanged C and H in the sentence.
No.
This is a shadow of a homotopy
I'm just
on the chain level, on the cochain level. You have a Frobenius.
Right?
It
won't transfer as a strict structure.
Yeah, that's why she gets the infinity structure on the chains.
No, other way. There's no. You don't know the Frobenius infinity structure on the cohomology.
No. I'm taking the strict structure on the cohomology.
Yeah.
That's why you said it could be the wrong one.
Oh.
Yes.
Well,
But that's.
what's it solving?
Oh, I'm saying these
Well,
are
you're
solutions.
choosing.
I'm choosing,
Okay.
and I don't know any other other thing to do. I mean, if you come up with something else, I'm happy.
Wasn't the first solution?
Oh yeah, I'm saying I know
Well,
these
you do
two.
know.
I know two solutions, but I don't know any other.
Oh.
Didn't Lambrecht and Stanley say their construction works over things much more general than just Q?
No.
I
don't-
No, that wouldn't.
No, I think they would. I mean, they have tried. Oh yeah, characteristic zero. Sorry.
Isn't it just Sullivan-Derham forms, this AM?
It's no, but the idea is to sort of. I mean, I guess the ideas are in something similar, but it's sort of fixing. It's I don't know if one can think of it as no.
constructed by instruction.
By
A kind of instruction.
Was it more complex? Okay, so in either of these cases, so I have structures which are essentially given by the prop of Frobenius algebras, and so if we plug in this into this machine, we're left to ask, well, what are these operations on the Rothschild complex of Frobenius algebras? And so this is something which was built on joint work with Craig Westerland, but there's also some partial results in this direction of Stradler and Alien, so they also misconstruct such actions also, and it's so for E is this prop of so by here I mean symmetric, the prop of symmetric Frobenius algebras, so the trace is symmetric. There's a split quasi-iso from these Sullivan diagrams I have not defined yet. Sullivan diagrams GPQ to these natural transformations, natural operations for this Frobenius prop from P to Q. So I better move on to saying what Sullivan diagrams are. So S, D, G, P, Q is going to be Sullivan diagrams. It's a chain. I'm going to define it here as a chain complex of Sullivan diagrams of type G, which is like a genus P, Q. So these are equivalence classes of fat graphs. Fat graphs are graphs with cyclic orderings at the vertices of genus G. When you have a cyclic ordering at the vertices, you can associate a genus, a surface, by thickening the graph. This is why they're called fat graphs, or ribbon graphs sometimes. You can thicken the graph, get a surface. You can look at its genus and its number of boundary components, so genus G and P plus Q boundary components. The last Q boundaries being embedded as actual circles in the graph. So example, there are two of these Q is equal to 2 here, and have two such actual circles, and then I have and these are boundaries, so I'm not going to touch them, and then I have a graph which is with cyclic orderings at the vertices, and it could be all sorts of complicated stuff, whatever you like. And then if you fatten this, you can count how many boundary components it has. It's a computation, and then you can do an Euler characteristic calculation, and you know what the genus is. There's an equivalence relation, and so these things have sort of, the edges are divided into sort of circle edges and chords, or sort of internal edges. So the circle edges are those that are on these particular circles. And you should think of these as sort of the ones containing the most information about the graph. The rest should be thought of as sort of length 0 extra information. And the equivalence relation says, equivalence relation is you can slide internal edges along each other. For example, a diagram like this is equal to, as a Sullivan diagram, to a guy like this, where I've done a slide of this edge along the other one. It's also equal to a guy like this, where you could slide.
So in your picture, you had one of those external, the tail on each component.
Yeah, sorry.
Is
Yeah.
that always there?
Yeah, I always have a start point, and I really also.
So can you? So that's how I can tell, because because if I look at your slide, I can't distinguish just rotating the picture 120 degrees to the left. If you see my. In the first of those slides, but if you mark a point on the boundary, then it's okay.
Are you happy? Yeah. So all my boundary components, they come with a start leaf.
Yeah.
So they will have this as part of the fat graph structure. Yeah. And a start leaf, if I had a start leaf here, then it can move with it. It can be anywhere.
Oh,
I guess
even the P components have starting leaves.
Yes.
Oh, which you didn't draw in the example.
No.
Okay.
Yeah. P's.
But you drew the ones
P0.
on the Q. Okay.
Yes. Yeah. I'm being a tiny little bit dishonest. Only a little
Still.
bit. I mean, there could be more boundary components. They could also be these could be open-closed things, right? I mean, they have sort of preferred I want P inputs and they're marked. I want Q outputs, they're marked. There could be other boundary components. Then I'm completely honest. Okay. Good. Okay, so these are these Sullivan diagrams. So let me sort of do on the side. I'll do a little aside to go back to remember this past, present, or future. So if we took, so again, this is a theorem that builds on work of a bunch of people. Costello here and Kontsevich-Sobelman. Although they don't formulate this way, but if you took E to be the prop, if you started in our sort of algebraic statement there, with E being the prop of open field theories, open topological field series, so where O, P, Q is a disjoint union over cobordisms from P intervals to Q surfaces, which are cobordisms from P intervals to Q intervals of chains on the moduli space of B diff of this surface. So do a big. This is actually okay. So you can build such a prop. You can define it in terms of graphs or something like this. What we get is this natural then these natural operations give you a disjoint union over surfaces which are now cobordisms from Q circles, P circles to Q circles of chains on moduli space of these cobordisms. So this includes, with a split quasi-isomorphism into the natural operations O, P, Q. And so the prop of symmetric Frobenius algebra, we talked about, this is H0 of O. You can identify these two things and the map over the map from O to the projection map from O to H0 of O, which is Frobenius, induces a map from these natural operations O to the natural operations of these Frobenius algebras, where here we have moduli space, chains on B diff, or however you like to call this, mapping into Sullivan diagrams. This is the map, how this natural map occurs. Now, if Ezra, you come up with some sort of interesting higher structure on cochains of the manifold, it may be that there is an interesting way of putting cochains on the manifold as an O algebra, which is not of the type I have proposed. I don't know any such way. And as long as you give me a way which in practice is something homotopy equivalent to the prop of Frobenius algebras, then what I get is operations that are parameterized by Sullivan diagrams.
Natalie?
Yeah?
Does that last statement hold only over the rationals, or would that also be true integrally?
This is integral.
That's
integral. That's integral. That's integral. Yeah.
I see. So the only place you use rational is to sort of strictify the cochain so you get an actual.
And Bruno tells me that's also integral. So if you want to do integral, I think that's also fine. Good. So there was one little thing I said when I said I wanted to construct operations. I just put one little condition, which was I wanted to not have the zero map. So it's good to know that you don't do zero operations. It's not that easy. So far, people tended to prove a lot of zero things about string topology. In reality, so when you look at this Sullivan diagram operation, so they are for every genus. We could take 0 and take 1. They exist class TG, which is a Sullivan diagram of genus 1 with one incoming, one outgoing boundary component. So this corresponds to a torus as a surface. No. Of genus, what am I saying? Wow. Genus G, genus G surface with one incoming, one outgoing boundary component, and a class, a Sullivan diagram G in genus 0, G plus 1 incoming, 1 outgoing. So these are both of degree 2G plus 1, so of higher and higher degrees, such that the induced operation on the Hochschild homology of the cohomology of the sphere, so this is isomorphic to the cohomology of the free loop space on the sphere, is non-zero on the class corresponding to the sphere itself in degree n, s n, for every n greater or equal to 2. So already just on looking at the string topology of spheres, we have two infinite families of operations that you can just compute and acting non-trivial.
What dimension is the, if you take this operation, is it TG? What dimensions does it have on? Like that class?
When I act, so I'll go.
Yeah.
So we'll take that class in degree n. It will go plus that degree 2g plus 1, but then minus so 2gn, I think. G is, yeah, I think that looks right. 2gn. I think that's correct. Yeah, so it's it was in homology. If you did it in homology.
Oh, I see. Yeah.
Yeah. So my Donna in homology. I'll go back to this in a second. Yeah, I'll tell you what. I still have time to tell you what it is. Yeah, just let me just. So.
Not negative all the time. N is big, isn't that going to be negative?
If n.
Maybe 8 minus or about that.
The class in my screen is up plus. I mean, okay, let's just, I'll just tell you what it is on the Hochschild complex, then I'm sure I'm not saying anything wrong. And then we can retry this discount. So I mean, the reason this computation is easy to make is that so these operations are defined on the Hochschild complex. Most boundaries, there's on the Hochschild complex of spheres, when the dimension is at least 2, there's only one class per degree, 1 or 0 classes per degree, and most boundary maps are 0. So the Hochschild complex is essentially already the Hochschild homology. And so it's just a question of checking which, what it does to one particular class. And what does the Hochschild complex looks like with the cohomology of Sn is just generated by, I'm back to my natural numbers if you don't mind. Generates by a single generator, which is in degree in degree n. When you look at the Hochschild complex, it has reduced. You might as well look at the reduced Hochschild complex, and elements in here are you have on the Hochschild complex of the cohomology of the cell. So for either even or odd spheres is actually the cohomology, the Hochschild homology, and for the other guys, there's every fourth guy there's a map which is non-zero, which is just a multiplication by 2. But elements in here, the generators are you have x, you have 1 tensor x, you have x tensor x, etc. Well, this x is representing now the class I was talking about, and the operation x, say, if we take tg, is going to send x to 1 tensor x, and this is where I have to count how many x's, and then we can count. That's what it does, and there's no sign issue because there's only one class it hits. And T1, I'd have 4 guys here, so for T1 this would be 3, and for T2 it would be 5, and then you tell me what the thing is, and so on. So you go +2 each time, and now the degree, the thing is, now this is isomorphic to the cohomology, but the degree counts, this counts as cohomological degree, and the Hochschild degree has to count as minus itself. So you get wait, can we count? So this is G. This is, I have 2G. I have 2G plus 1 guys. 2G of them are, I have this 2GN, which is these 2GN guys. I'm screwing this up, but it's definitely not in negative degree. It is an existing guy, Okay, Oscar can work that out. He's happy. It is that bad formula. Good. I just wanted to say one more thing here is, maybe 2 things. First, this is where I like these examples because they lie exactly where we knew the degree 0 operation, which is the same in the old string topology and the BDIF string topology than it is here. The degree 0 operations we knew was 0 in these cases. So the one corresponding to higher and higher genus surfaces, we actually know this is a result of Tamanoi. We know that these are 0 operations. And same if you have too many outgoing boundary in string topology, in the homology of the free loop space, they would become coproducts here, and we would also know this was 0. But I'm in higher and higher degrees. So these are sort of higher operations where things were trivial at the bottom. And the other thing is a little corollary of this is also that these classes TG and UG represent non-trivial homology classes in Sullivan diagrams. So as Sullivan diagrams, I can easily check their cycles, but I cannot easily check their non-trivial homology classes. And so this is really a way to use representations in the way I wish I could use it for mapping class groups. This is a very simple example where we do actually detect homology by acting on something. Good. So I promise to come back to a geometric interpretation. When you're talking about operations on the free loop space, it should have something to do with loops. And so one could describe this. So this is the geometric approach, and this is joint work in progress. with Ralph Cohen and Nancy Kingston. And what I'll, because it's in progress, we'll just do an example, right? The example will be good enough. So at the same time, we'll illustrate what these classes are. So let's take T1 in the last theorem there. T1 is represented as a graph. It is just is the graph. So this is, I mean, as a Sullivan diagram, this is the graph T1. So what do I know about it? This is well, it's a I mean, you can compute. You can look at, if you like. It's just for the sake of it, check that it has one. It has one boundary component, which is the sort of well. Now we'll do the operations the other way around. This will be our incoming circle here, and then there's another boundary component which goes around here. And if you compute the Euler characteristic, you'll find out that this is so as a surface. This is a surface. This is a torus. A torus with two boundary components. And as a Sullivan diagram, has degree 3. The degree was the number of edges on the circles minus 1, so this is a degree 3 guy. And then what I said is that it's a cycle. So these are the things I know. But I mean, the sort of, if you're now sort of back into the minds of string topology and how the Char-Sullivan product was originally defined, you should look at this picture and say, so we want an operation from the homology, or maybe chains on LM to chains on LM. It has one input, one output, and it should take a class, and it should somehow, I mean, this picture is telling me you should think of your original loop as the sort of the guy which is here, which is on the outside. This is your original loop, and this picture is giving me an intersection pattern. It's saying I should intersect this here, and I should intersect that there. And then the green is telling me how to read off what I get as a loop in the end. So I mean, what the important information is an intersection pattern. And what the operation is going to do is going to take a class, so a chain here in the loop space, and what we want to do is you want to first cross it with a copy of the 3 simplex, which I'll then fold on itself in a particular manner, and then I want to, I'll show you the 3 simplex in a second, and then I'll do this intersection pattern which says I should intersect with loops that intersect in this manner, in the same way as we intersected loops that were a priori anywhere to loops that were meeting at a certain point. So maps from, I can't draw such an intersection for a loop, so I'll just draw it like this into the manifold. So I should say more. So let me show you the 3 simplex to start with. So the fact that the Sullivan diagram is a degree 3 Sullivan diagram is actually exactly, I mean, in this case it is really just a copy of the 3 simplex in a space of Sullivan diagrams. So the 3 simplex is just the choice of the placement of these points on the circle. So here's my T1, T2, T3. So I have a copy of the 3 simplex, which is choosing where these points are, and then I said the boundary of this diagram is 0. It's a cycle. What's the boundary of T1? Well, it's the sum, maybe I didn't say this, the boundary maps in Sullivan diagrams are sum of collapsing edges along the circles with alternating sides. So if I compute the boundary, I'm going to have something like this minus something like this plus this guy, Ezra is going to complain, and then minus this guy. And now I told you in Sullivan diagrams I could slide along edges, and so you see that these two guys are equal, and I could slide here, and so these two guys are equal. So this is a zero boundary. But what am I doing with if I'm thinking in the 3 simplex delta 3, I'm looking at the 4 faces, 2-dimensional faces of this 3 simplex when T1 is 0 and so on and so on. And this is telling me I should identify phase 1 with phase 2, and I should identify phase 3 with phase 4. This is what so delta 3 mod this equivalence relation. The equivalence relation is phase 1 identified with phase 2 in this particular prescribed way. This is a precise description of it, and F3 identified with F4. So this is now, and this doesn't have any boundary anymore. This is, I'm crossing with a 3-dimensional thing there, okay? And then what is this maps? The maps, this is now, I'm living in, this is now in loops cross coordinates, and to be honest, I'm going to work with loops parameterized proportional to arc length, and these are then telling me points on the loops, and these things are, elements which are loops plus coordinates such that when gamma T1 equals gamma T3 and gamma T2 equals gamma 0. It's a loop with a particular intersection pattern. So the tricky part I said was more tricky in the geometric picture is actually to do this intersection. And so we have to fiddle around a little bit, and I'm going to spare you the details. I'll stop here.
Can you say something about the commutative Sullivan diagrams?
I don't know if I'm allowed. I didn't ask Angela. Yes, let me say just a little. We don't understand the full picture yet. We don't know exactly what this is. We'd like a small thing it is quasi-isomorphic to, but we have a sub-family which looks very good with respect to the geometric picture, which is quite simple. If you look at the Sullivan diagrams, what's a commutative? Your first guess of a commutative Sullivan diagram is you forget this. No, I don't have. If this had been a vertex, or maybe this is a vertex, you forget the cyclic ordering, which is not the cycle. So you do that, but that's a useless thing because you can't define anything with those. But then you add an extra piece of information, which is a choice of a loop. Sort of from your base, I don't have any base vertex. Here's your outputs, from your output to itself in this space, in this cell complex. And the choice of a loop, if you think in the geometric interpretation, is actually just choosing, once I have done my intersection pattern, I have loops that intersect in a particular manner, I still have the freedom of choosing how I evaluate, which loops I decide is my first loop. If here I get sort of 4 bubbles, I can take them all, I could take only 3 of them or something. I still have a lot of freedom.
How is this related to, is this at all related to moduli spaces of graphs or automorphism groups of previous boundaries?
There's map, she sees this, she saw this completely on the algebra side, right? So and on the algebra side, I have maps, right? Obviously, but anyway, Sullivan diagrams just map. So modular space maps via Sullivan diagrams via these things. And I don't know. There's a little more. There's a lot of stuff. but it's the beginning of the picture.
Did you try to look at you have other combinatorial models coming from causality theory composed black and white graphs, for instance, something like that? You try to look at action like this?
Action like, I mean, these are. I mean, you could. I usually when I work with Sullivan diagrams, I write them as black and white graphs. So I don't know. I mean, this is the original type of picture. This is why I drew them like this. But I mean, this circle is really. If you write it as a small vertex, then it behaves like in a chain complex. I mean, I don't know. Then the boundary is a blow-up boundary, as you usually do in chain complexes.
With black and white graphs with black and white vertices.
Another question?
And can you do the same thing for higher loop spaces? I mean, the maps from Sn to something where n is greater than 1. Can you do the same procedure just?
I mean, there's some, I mean, so there are some things. I mean, not. What can we do? I mean, so there's a student Angela Clapp. What she did is to work with. So she looked at commutative algebras. In the world of commutative algebras, she looked at high Cauchy homologies in the sense of Pierre-Schwili, and there she can run this machine. So I mean, as soon as so you can run this, and then this becomes a sort of you're looking at. Instead of P and Q here, you should think one simplicial set and another simplicial set, and then you may, and you can build this construction, and you can ask what it is, and if your simplicial set is of lower dimension than the connectivity of the other guy, then this is well behaved. This is a map. This is equivalent to the mapping space of the simplicial set. But if these guys are of the same dimension, you get into trouble. So we can do a little bit, but it's not easy. It's a bit messy. I mean the loop space being.
What do you know about stabilization in static diagrams?
Stabilization?
Yeah. What is the loop completion?
I don't know.
You get into you get into
I don't know. I haven't solved one at all. I know nothing. Yeah.
Can I ask, what do we know about the difference between the homology of Sullivan diagrams versus moduli spaces?
I know, so one thing is I know all the stable homology dies. I mean, anything, I mean, and somewhat more. So a lot of things die, but I mean...
Do new things appear?
Yes, I mean, these classes, I don't know all of them. I mean, the only one I really have looked at very precisely is the sort of the one here, which is equal to 1 is corresponding to a pair of pans, where if you take a pair of, so Sullivan diagrams are asymmetric. Right? It depends, it's very important which is your in or out. And one way around the pair of pans is the Sullivan diagrams for the pair of pans, if you have two circles in Sullivan diagrams, this is isomorphic to moduli space. If you only have one circle in Sullivan diagram, this is, instead of moduli space, which is S1 cross S1 cross S1, you get S1 cross S3. And this guy is the S3.
Oh.
And I suspect all of these are of that type, that they are sort of, they're built from, they definitely correspond to families of degenerate, surfaces that become degenerate. But there must be some unstable homology. I mean, you'd say the map is not trivial. But I don't know.
And do the Sullivan diagrams form a prop?
Yeah. I mean, and these are maps of props. I mean, one way of defining a prop of moduli space, chains on moduli space, is to, you can make a description where, to make this prop on the level of chains, so that is with a graph a graph description, you really, the only thing I know that works is exactly to have sort of embedded circles like this. And on one side, you can assume that that half of your that either your input or your outputs are embedded. And now the map is just the quotient, and the gluing is the same. The fact that it's because you have these embedded circles that you can do the gluing process.
Is there a way of seeing directly the action on the homology of the free loop space, because there's somehow a duality? You get actions on the cohomology of the loop spaces, but one would have if I understood well
yeah. I mean, in some sense,
on the cohomology of the free loop space, but one would like to have directly actions on the homology of the free loop space.
it's just that you would like to have a geometric construction of these things.
Yeah.
And I mean, I should say also, I mean, in the case of the Chas-Sullivan product, it was proved by Felix and Thomas, I think, that the Chas-Sullivan product, this geometric construction, is equivalent to this homological algebra version of it. I mean, so in Haussian homology. But I mean, Russian. So they only do Russian things.
May I suggest we defer further discussions to Bob? Thanks, speaker again.